Okay, let's talk about the patterns and trends in the periodic table. You'll see that the main patterns are all very related. So we have atomic radius, electronegativity, and ionization energy. We're not going to talk much about melting point because there's really not much of a pattern here. But look at this here, atomic radius, as you go down, the darker color means it gets larger. And so go down, it gets larger. Go this way, it gets lighter, so it gets smaller. Electronegativity and ionization energy are both opposite from atomic radius. As you go this way, it gets higher for both of these, and as you get further over here, it gets less and less. So what it means is the following, folks, is that atomic radius is the size of an atom, and electronegativity is how much an atom wants electrons when it's bonded to another atom, and ionization energy is how much energy it takes to pull off electrons. So what you have here is that these two are very similar and this one is opposite. Let's talk a little bit about that. If we look at the atomic radius, you'll see that as you go down, it gets larger, and as you go to the right, it gets smaller. Look at that general pattern here, okay? So what happens is that as you get smaller, the atom is pulling on its electrons, and you could think of it as the positive nucleus pulling on the negative electrons. And as you go to the right, it pulls on them tighter, and it's smaller, and it's harder to pull off those electrons. So the ionization energy is higher, and also the electronegativity is higher because it's pulling on electrons. If you put another atom on here, it's going to pull those electrons as well. So you can think of it as you go to the right, atoms love electrons more. As you go to the left, their attraction for electrons is less, both their own and their neighbors. And that's seen right here with electron negativity and ionization energy. So as you go up this way, the energy to take off an electron is higher, and as you go this way, as the size gets larger, the attraction to both their own electron and other electrons is less, because it's just easier to pluck off electrons the larger it is, and harder when it's smaller. I think of this as the stealing candy from a baby. Actually, babies are pretty strong. They're small. You try to take candy from them, they hold on to it really tight. If you try to steal candy from a larger kid that has their hand out here, it's easier to take it. I don't know if that analogy works, but it's fun to think about. The best way to think about explaining this is the following. Let's talk about shielding. First thing first, let's talk about the size as you go down. As you go down in the periodic table, there are layers and layers of orbits of, let's call them orbitals of electrons, and they actually take up space. So you could see that as you go down, the atom gets larger. And here we use a Bohr model. It's a pretty good model to think about shielding with. So as you go down, the electrons get further away, and the attraction between the positive nucleus and the outer electrons is less for two main reasons. One, it's further away, so it's easier to pull those electrons off. And two, there's all these other electrons in between that are blocking the positive nucleus from the outer negative electrons. It's as if you're at a school dance. If your electrons are nearby, your attractive force is strong, you're going to hold on tight, so it's really hard to pull off that electron. So the ionization energy is really high. If your electrons are further away and there's layers of electrons blocking you from them, it's going to be easy for them to take off and go off with another, to be stolen away. So the message is stay close to your electrons if you're a nucleus, especially when your song comes on. The different pattern is that as you go from left to right, the atoms actually get smaller. And what you're noticing is that the electrons in between the protons and the electrons are the same. So the inner electrons don't change. So they're blocking the inner and the outer the same way. The only thing that's changing is the number of electrons and the number of protons. As you add more protons, it pulls on to each of those electrons more. So I think of it here, you have less protons here. As you get more protons, it pulls it in tighter, and it gets smaller, and it gets harder to pull those electrons. So that's really why you end up with this pattern here, that as you go from left to right, there's more protons pulling on those electrons, making it tighter, harder to pull off, and then when their attraction for their own electrons and other atoms' electrons is really high. Over here, it's larger, it's further away, it's easier to steal electrons because their attractive force to those electrons is low, and you get another atom their attractive force is going to be low to their other atoms' electrons, just as they are for themselves. Cool. The final pattern is thinking about the atomic radius, and you can explain it via the same logic. As you have an atom here, take a look at fluorine versus F minus. The size here is 0.072 nanometers. F minus is 0.136, almost twice as large. You have the same number of protons, and if you have more electrons, they take space, they're going to repel each other, and they're not going to have as strong of attractive force if there's 5 electrons versus if there's 4. Okay? So really, it's you add more electrons, they're more negative, they take up space, and it kind of like stresses out the pooling ability of these positive protons in the nucleus. The opposite is true with positive ions. Normally you have a strong attraction here with these protons, these electrons. You get rid of one, it pulls. Now these 5 protons are going to pull on 4. They can pull on each of those a little bit more and tighter, so it gets smaller. So you'll see that all of these positive ions are way smaller than their regular atom by itself. Okay? Cool. There you go. Hope that helps.